Hey guys, in this video we're going to learn about torque and angular acceleration. Throughout this video we're going to refer back to a couple of equations. One of them is that the sum of the torques equals I alpha. Remember, I is called moment of inertia, that's resistance to rotation, and alpha is the angular acceleration of the object. Most of the time we're going to look up moment of inertia in a table, which is in your textbook on page 304. The other equation that we will use frequently is torque equals F cross R, which remember is often going to be expressed as FR sine theta. Cross products are proportional to the sine function, and that's what that X there means. The F in the equation, F cross R, is the force which is causing the rotation of the system. R would be the distance from the pivot where that force acts. And then we'll look at the sine function in the context of a few different specific examples. The other equation that we're going to use throughout this video is called the parallel axis theorem. This is the one that you use whenever you're trying to find the moment of inertia for an object that is not rotating through its center of mass. The ICM part of it is the moment of inertia through the center of mass. M is, of course, the mass of the object, and d is the distance between the center of mass and the pivot point. Remember, everything in rotation is always relative to the pivot point. D is specifically between the pivot and the center of mass of the object. We're going to start on this page in your notes with example 5. In part A of the question, it's describing rotating a rod, but it's not rotating about its center of mass, which is presumably right here in the middle. Rather, it's rotating about a point which it says is L over 3 from its end. Well, we get to pick which end we're talking about. So how about here from this end? And so that distance is L over 3. Wonderful. All right. Now, first thing would be it's asking us for the moment of inertia. And we might look at it and say, oh, it's a rod. Got it. I'll just look that up in a table. Not so fast. It's not rotating about its center of mass. So you can't just look it up in the table. Well, Mr. Errico, there's this other one in the table, which is a rod rotating about its end. No, sorry, it's not rotating about its end either, right? It's rotating about that point right there, right? That's the pivot. So there's actually no way to find the moment of inertia except for, oh wait, what was that last thing? Oh yeah, it was the parallel axis theorem. That's the one you want to use. Moment of inertia through the center of mass of the rod is 1/12 ml squared. I'm going to have you pause the video though and real quick figure out what do you think D is, and then see if you can come up with the correct expression for the moment of inertia for this system. So pause me. Try that out, and then resume once you think you've got it. All right, now one thing people will do here, easy mistake to make, is pay too much attention to what they have said in the text, right? They said, oh yeah, L over 3, and you're like, oh, it's a distance of, D is for distance, of course. D in this equation is not distance. I mean, it is a distance, but it's not always the one that they tell you. It's the distance between the pivot and the center of mass. All right, well, there was the pivot, and here's the center of mass. That is not L over 3. That's not the distance that they told us. So if you're not sure how to get that, you might think about the fact that this distance is half of the length of the rod, because the center of mass is presumably in the middle of the rod, unless it's really weirdly weighted or something. All right, and that means that the remaining distance between those is the difference between L over 2 and L over 3. 1/2 minus 1/3 is in fact 1/6. And so that's what should go in for D. All right, next line down, when we simplify, we're going to get 1/12 plus 1/36. All right, so 1/9 ml squared when all is said and done. All right, that's part A. Wonderful. The moment of inertia, though, remember, does depend greatly upon where exactly you put the pivot. Part B is asking us for, now, a different pivot point, right? It says rotating the rod about its end. This is one you can look up, but our goal here is to show why it is what it is. So we'll start with the parallel axis theorem. And in this case, it's a bit easier to say what D is. D would be half the length of the rod. So, because the pivot's at the end, center of mass is in the middle, d is the distance between those 2 points, so that means that we would have L over 2 for d. All right, that's going to give us 1/12 plus 1/4, and if you do a little bit of algebra there, you can determine, oh hey, that is in fact 1/3 ml squared, which is in fact what it says in that table in the book. All right, awesome. Next part is another common kind of question where they're going to ask you to determine the angular acceleration of a falling bar. So let me erase some of the clutter here so that we can read everything. If we want to find the angular acceleration of the falling bar, we're going to have to use the concept of torque. So if you remember back to the beginning of the video, I said the sum of the torques equals I alpha. And we calculate an individual torque using that formula F cross R. So we've got to figure out what force makes the bar rotate in the first place, and also where that force acts. All right, well, those I think are two fairly straightforward questions. Seems like pretty obvious that if I hold this bar out horizontal, allow it to pivot about the end, the force that makes it fall is, of course, gravity, right? And there's gravity acting on it. Okay, so then if I plug into my torque equation for F, that's just going to be mg. Wonderful. All right, now take a minute and think about what you should put in for R. So pause me and then think about it. A lot of the time, people will put in L. They'll just put in the whole length of the rod, right? The whole thing is a length of L. But actually, the force of gravity is acting at the middle of the bar. So in fact, I should put in L over 2. That's probably the #1 blunder on this type of problem, is that people would just straight up put L. And the reason that they do that is it's purely psychology, right? If you were watching this thing go wee, swinging around like that, you would be not looking at the middle of it, right? You wouldn't look here at the middle. You'd look at the end, right? That's what your eyes would do. You look at the fastest moving point on that bar. And so psychologically, you think gravity's going to do the same thing for some reason. Well, gravity doesn't think like you do. Gravity acts at the center of mass, right there in the middle. Gravity's like, what? I don't even care about the end. It's all about the middle for gravity. So if you want correct answers, you've got to think like gravity and always consider the force of gravity as acting at the center of mass, not at the very interesting to you end of the bar. All right, well, a little bit of algebra later, and we should be able to get that alpha is 3g over 2L. Wonderful. There's our answer. All right, so that's the angular acceleration. D is asking a useful follow-up question. They're asking about the linear acceleration of, and then various points on it. It is very common that you're going to be asked about the linear acceleration in addition to the angular acceleration. Or maybe they'll even ask for the linear acceleration and not even say, find the angular acceleration. You'll always need to find the angular acceleration first. But once you've got it, it's just a matter of using this equation that we've got from the beginning of the unit. The linear acceleration is equal to the angular acceleration that we just got times distance from the pivot. What's distance from the pivot? Well, it depends which point on the rod you're asking about. For part 1, they're asking about the center of mass of the rod. So the acceleration of the center of mass can be found by doing alpha times, well, the center of mass is L over 2 away from the pivot. Factor of L cancels, and we have 3g over 4. All right. The center of mass is not going to experience the same acceleration as the end of the rod, though. If you want to pause me and preemptively figure this out, go ahead. All right, it's a little different because R is different. The distance that the end is from the pivot is just L. And so we get 3g over 2. All right, that's it for that particular example. So that should enable you to answer any falling bar problem. Wait, Mr. Errico, What about sine theta? You never did anything with sine theta, and I remember that f cross r means it's a cross product, and so I've got to do something with the sine function. Why didn't you ever do that? Well, the reason I never did it is because, what's that angle right there? Yeah, that angle right there. Well, that's 90 degrees. Sine of 90 is 1. So you only need to worry about the sine function if your bar has, say, like fallen some distance, right? So there's the bar having fallen some distance. Gravity stays straight down. The radial vector points always towards the center of mass from the pivot, right? And now this angle is not, that what looks a little bit like I was trying to draw a box. There we go. That angle is not 90 degrees. And so in that circumstance, you would need to use sine of whatever that angle is. Note then that that means that the angular acceleration is always greatest when the rod's in the horizontal position, because sine of 90 is the max value. All right, on to Pulley problems. Find example 8 in your packet. I'm going to vastly simplify this question for the purposes of this video and introducing you to Pulley problems and torque. I'm not going to use this image at all. I'm going to completely get rid also of the text, right? The question that you're going to be asked here is simply this: find the acceleration. So that's it. We're going to find the acceleration of the hanging mass. Well, this is going to involve a throwback to forces and also an application of our new knowledge about torque. So the forces acting on the hanging weight would be gravity and the tension. Well, everybody pause me and take a minute to write the equation for the sum of the forces. Ta-da! Easy, right? Mr. Erico, I have T minus mg. Is that okay? No, that's not okay. Remember, the largest force goes first. It'll be accelerating in the downwards direction. Therefore, you want to have the force of gravity being greater than the tension force. The other concept that you must use here, though, is the concept of torque. You can't describe the rotation of the pulley without thinking about the torque that's acting on it. This is where people usually go wrong, because they're going to get the wrong equation for the torque acting on the pulley. So I'm first going to write this in red for wrong. I know wrong technically starts with a W, but this is incorrect. Maybe I'll label it. All right, so everything I'm writing right now is incorrect. Here's what people's reasoning is. Well, see, the reason that the pulley rotates is because of gravity, right? Doesn't gravity make it rotate? Sure, yeah, that makes sense. All right, so I know that torque is F cross R. Okay, that's actually fine. Torque is F cross R. And so, if the force making it rotate is mg, let's see. Well, the radius of the pulley, I guess I'll use R, okay? There's the radius of the pulley, right? It's R, wonderful. Then that would be the torque acting on the pulley. And I'll set the sum of the torques equal to I alpha. All right, now some things here are fine. I'll say that, yeah, saying that the sum of the torques is I alpha, yep, that checks out, that's okay. Here's the problem, the whole problem right there. Nope, sorry, gravity isn't what makes the pulley rotate. To understand why that is, let's think about what if you cut the string? The pulley's not going to rotate. The weight will fall, right? So gravity is what makes the weight go down. But the thing that actually makes the pulley rotate is the tension. It's not the weight of the block, okay? The tension in the string is the reason why the pulley actually rotates. So instead of mg there, we should have the tension. So the torque really should be tension times radius. That's what we should have. Well, hear me out, Mr. Erico. Won't I get the same answer if I put mgr instead of tr? Because the tension and the weight are the same. Look at the first equation you wrote. They are not the same. The weight can't be equal to the tension. If they were equal, the weight wouldn't fall, right? It would just hang there. It'd be happy. Okay, so now that we've got all that out of the way, right? It's the tension that makes it actually rotate. Now we can start actually solving this. Well, so the next step in this is to recognize that we have both A and alpha in the problem, and we can only work with one or the other. Fortunately, we know that A equals alpha R. So that means that I can replace the alpha with A over R. So let's do that. The moment of inertia could be a lot of different things. Mostly, though, it's going to be one of the cylinder formulas. In this case, we'll say that it's a solid cylinder, which if you look up that moment of inertia is 1/2 mr squared. I'm using a big M here because I'm going to say, what if the pulley is a mass of big M? That's just what we're going to call it. All right, so 1/2 big mr squared because it's a solid cylindrical pulley. Now, when we do the algebra here, what we're going to discover is this radius cancels one of those. And then if I divide both sides by radius again, the radius of the pulley actually entirely cancels out. That's going to be true as long as the string is wrapped around the edge of the pulley, which pretty much in every circumstance in this unit it will be. But just hypothetically, the radius wouldn't cancel out if the string was wrapped around some other point. All right, now I've taken my force equation and rewritten it down here. And this should look real familiar from not last unit, but forces, way back when. Use elimination. The tension will cancel out, will eliminate. And now we have this. Ta-da! And if you wanted to solve for, say, the acceleration, then you'd do some factoring, and you could divide on over, and you would end up with this answer. There's more that we could ask with this question, more that we could answer, but once you know the acceleration, you can get most everything else. Like if they want to know the speed after some amount of time, that's a kinematics question. If they wanted to know the distance it travels in some amount of time, that's also kinematics. So often kinematics is the next step here. I'm not going to cover that in this video because by this point you should already know how to do one-dimensional kinematics. I did want to explore one other hypothetical before I end this video, and that's what if it were like a cylindrical shell for the pulley with, like really lightweight spokes but a heavy rim? Well, if they're having you say that it is a cylindrical hoop kind of a shape, the 1/2 would go away. So this 1/2 depends on what type of cylinder it is. So if it were a hoop-shaped pulley, then all those 1/2s would go away. And then they might ask you sort of a conceptual question here. How would this change the acceleration? Well, if you think about the math here, if you are now dividing by a smaller number because you got rid of that 1/2, dividing by a larger number because we got rid of the 1/2, this would give you then a smaller acceleration. So if it were a hoop, then we would get a smaller acceleration, assuming, of course, that the amount of mass that's in the pulley stays constant. All right, that's everything. I'll see you guys in class. Thanks.